which is supported and sponsored by the School of Civil Engineering at Southwest Jiaotong University, which with the aim to invite international scholars to present their latest to students and research civil engineering. And we, in the key lab of highway engineering of Sichuan province, we decided to provide a series of lectures on sustainability and resilience of transportation, infrastructure, materials, which hopes introduce as one of the, in fact, this topic is one of the topical subjects and which had attracted many attention of many scholars and researchers in recent years globally. And we hope this lecture series introduce a paradigm for production, characterization, and modeling of asphalt materials as one of the widely used construction materials in transportation infrastructures. And we hope this lecture series encourage and students and researchers to make up ideas for their future research. In this today's presentation, the session 2 of part 3 of this lecture series, the topic is about do all rejuvenators revitalize aged asphalt? And the speaker and the presentation of this lecture series is one of the global expert leaders and pioneers of sustainable novel materials for use in construction of transportation infrastructures, Dr. Ellie Fini, which is now currently serving as an associate professor at Arizona State University. She's also an invention ambassador at the American Aalborg University of Denmark, a senior sustainability scientist at the Global Institute of Sustainability and Innovation, and director of the Innovation Network for Materials, Methods, and Management. And her research mainly focused on the production, characterization, and atomistic modeling of sustainable novel 200 scholarly papers in peer-reviewed journals, women in STEM, and also the top journal of resources conservation and recycling. And she has served as the president of ASCE North Carolina Northern Branch and a program director of the National Science Foundation. And in recognition of her achievements and her dedication during her career, she won many awards such as NSF Career Award, ASCE Gerald Seeley Award, BR Emerald STEM Award, and which shows that her dedication, her contribution to the field of sustainability and use of novel biomaterial in road construction. So we really appreciate Dr. Fini for accepting our invitation, and it's a privilege to have her to present her research works. And before I pass on to Dr. Fini, I would like to mention everyone that please during the presentation type and send your question to me directly. At the end of, I will collect the questions, and at the end of presentation, I will read the question, and Dr. Fini will respond to the question. And also, I would like to mention that our last session will be held on December 27th on about the mechanism of moisture damage in asphalt. I hope the people, all attendees will also will be attend our last session of this lecture series. With that, I will pass on to Dr. Fini, and we very welcome her. Thank you. Yeah.
Thank you for the introduction, and hello everyone. Good morning, good afternoon, wherever you are listening to this talk. Hope you have a good day. We're going to talk about something which is quite interesting to me and my group, talking about aging and rejuvenation. So before I actually start talking, I want to make you think about what it involves aging and what we consider as aging. I know in science, we refer to aging and we measure aging, we quantify aging, but in vocabulary, aging is actually a very known concept. I guess by every birthday, you yourself are getting aged. So aging is actually an indication of time passed from the start of or creation of a material, where it's the same thing, I guess, in human being. As you get aged, your skin gets aged under sun, and your bones get aged. Those are all mechanism of degradation. So we're not talking about material. So when you look at the surface of an asphalt, which is one of the built environments we create as human, we make them, over time it gets aged, and you sort of can say if this is a brand new asphalt or is an aged asphalt. It doesn't really need as much of science to look at an asphalt and figure out if this is a new piece of road or it's been there for quite some time. Well, of course, there are signs. So I want every one of you, think about that and maybe put in the chat box what you think aging of material involves. What is that? Something is aged or is not aged? Take a minute to just think about it, because I want you to recognize when the aging happens, material is changing. Sort of like we can't go back to when we were a baby, we're older, material get older as well. So aging is involves several mechanisms. On appearance, that's something. So when you look at an asphalt road that is freshly paved, like you go home and you come back tomorrow, you see a brand new, nice piece of road on the drive to school. After many years, that road changed color, changed shape, maybe crack, maybe ravel. So 10 years back, when you look at that same piece of road, it would look different. So yes, look could be one indicator, but I always tell my student, and I want to tell you guys the same way, when we think about it in science, you always look at the problem first, then look for tools. I mentioned this in the last lecture, that don't worry about the tools. We find tools to measure a phenomenon and a concept that we think it's happening. But first you have to actually think about that, what you want to measure, what you want to prove that is happening. So in this case, just looking is one measure. If the road is different color over years, that's one measure of aging. I'm going to tell you much more and maybe more sophisticated tools to evaluate aging. So I put it in this picture here, and you can see the one on the all the way to the right, it seems newer. It seems much more together and in a better shape, versus the section on the left, it seems more aged and degraded, and it doesn't look as together. So from the left side to the right side, there are differences. You can just look at it. So now I'm going to show you a bunch of other methods to tell you that this piece is aged or how aged. And then the next step, which I want to talk about today, is can we restore it? Like if it was in the case of human being, can I make you go back 10 years? Well, I can't. But in terms of material science, we have some ways to make material look younger, which sometimes I use the analogy of all this, makeups and creams and rejuvenators that we use on our skin to look younger. So same thing with the material. We can make it look younger. But one thing that I want you to be very cautious about and careful is not literally not uncook it when it's cooked. So some of the chemical indicator that I will show you, and you may have seen or you may see in future that some authors have reported as undoing chemical interactions, sometimes is impossible. For instance, if there is an oxidation happening, oxidation process is almost not practical to take away the oxygen that already reacted with your material. But on the physical sense and on the mechanical sense, we can restore the properties. And when it comes to engineering and engineering of road especially, we think about performance. So even the chemistry is changed, as long as I can get the same mechanical performance, whether it's crack resistant, elasticity, viscoelasticity properties, crack healing, if I get all of those as good as it used to be, then it's good. I can call it rejuvenation. So I'm taking a bit more time on this single slide because there is so much embedded in this single picture. One is you need to understand the aging mechanism if you want to reverse it or if you want to improve your aged material. And I will show you at some point during this lecture that, well, sometimes it's just too late. You cannot literally undo things. And maybe aging is so progressed that rejuvenation would not make as much of a sense at that point. So let's get started and talk about rejuvenation and aging. As Ali mentioned, if you have any question or you think of some topics of your interest relevant to this, as I talk about this topic, write it in the chat box so I leave enough time at the end for the discussion. So Ali already went through the introduction, but I put my email address in the bottom here. If you have any question or you want to follow up, you are always welcome to email me. So you look at this material I put in here, and it seems something is spraying on the road, and we call those rejuvenator. You may hear a lot of different rejuvenators these days in the market trying to restore and revitalize asphalt, aged asphalt, so they allow or enable the recycling. So the topic of this discussion is actually for you to think if any modifier out there is a good rejuvenator, or it can even rejuvenate an aged asphalt. So let's start by looking at what aging does to our material. So much like I mentioned your skin, asphalt has its own skin. So look at this sample on the left. It was just brand new cast of bitumen. We put it under aging process, and now you have the one on the right. You can see the skin of that on the top surface, the cracks, and change of shape to some extent. That's the aged one. Let's see what happens aside from look. I told you there are many different tools, so I wanted to show you a bunch of tools. Right now on the top picture, right now here, it doesn't need much of a scientific tool. My eye and your eyes is actually a good tool to say the picture on the right and the one on the left are different. One is aged, one is not. So now let's look at more sophisticated tools. So one element of aging is actually changes in chemistry. What happens with the progress of time and oxidation? Oxygen is in the air, so it combines with your molecules in asphalt, and it forms oxygen bonding compounds like carbonyl. Here you can see the carbonyl that was measured by Fourier transform infrared spectroscopy, FTIR, that most of you are familiar with. And we calculated the increase of carbonyl over the aging time. So if the material would not age at all, like nothing happened to it, then the carbonyl index will not go up because there is no more oxygenated compound. This carbonyl is basically CO compound. So you have the combination of oxygen that is now bonded with carbon. So you have these carbonyl groups that are going up as the aging progresses. Initially, you see a big jump, and then the increasing rate will be slower, but you still keep seeing them going up. We only went up to 200 hours, which was still pretty severe. And we stopped right there. You can see how it goes up. And then we looked at mechanical indicators. So as I mentioned, one indicator is just my eye looking at it. Another indicator here is chemical indicator based on FTIR, and the mechanical indicator based on crossover modulus. So you can see at the beginning, the crossover modulus of the sample, the aged one is up there, and then at 20 megapascal. As it ages, crossover modulus start dropping, initially much more, and then it slows down, but it still keeps going down. Here in this figure, there are two different patterns. You can see black and green. One has anti-aging, one doesn't have anti-aging. We'll talk about it in a minute. But regardless, if you have anti-aging or you don't have an anti-aging, you cannot reduce it to zero. Almost there is no material that does not age at all. You can slow it down, you can reduce the rate of aging, but as you can see here, the one with the green, which has anti-aging, also ages. The difference is it ages slower and it stops at a much lower, higher modulus. You can see like at 16, the other one keeps going down. So you can see the rate is reduced, but you cannot bring it to zero. None of the anti-aging I have ever worked with make it to go to completely no aging. So it is anti-aging, but really it means it's slowing down the aging. So what happens in a more sophisticated, so one level down. Now we're getting to more molecular side and macroscopic in nano scale to see what's happening at that scale. So here we are looking at the results of atomic force microscopy. And many of you may be familiar with the features we're talking about here. Typically in asphalt, they are referred to as bumblebees. Those little features here you can see. We have published, and our position, our group's position is that these are wrinkled wax structures that are separated from the rest of asphalt. But regardless of what their source is, this talk is not about the BS structure and what they are made of. But for those of you who are interested, you can look at some of the paper we published on the origins of bees and how they change over time. This talk is just about aging. So you can see this material, and as we looked at different location on the surface of the material, and then here we plotted the IR spectroscopy. This was a nano IR, which we could look at microscopic feature and at the same time chemical mapping. The paper, I put it here for those of you interested. The chemical mapping of a UV aged thin film sample, actually here, it shows that there is a difference between different phases. So paraphase here, the black dot, paraphase, periphase, and the red one, paraphase, are very different. You can see here. But One big difference is actually surface and bulk. You can see the green, which we measured with ATR, FTIR, and the black, which we mostly measured the bulk, and they are very different. So what you actually see on the surface here on the top, the picture I showed you first, it shows you the surface, but it doesn't tell you the whole story about the entire material. So if you think about the bitumen being few micron, or in this case, we have actually thin film. On the top, we have a different characteristics as it shows with this FTIR. The black and red are on the top surface, this one, and the green is the bulk, and you can see they are very different, surface and the bulk. So one more level of measurement is, if I see aging, how much aging happened, I can say with this. So I can measure how much aging. With this, I can say where it happened. Is it just on the surface, or is also in the bulk? Are they equally aged or not? So I caution you, if you look at aging and get into the study of aging, be careful on the depth variation, because as I showed you here and we published in this paper in ACS, the depth, the downward inside the bulk is a different story than on the surface. Clearly shown here with the two spectra, one on the top, one in the bulk, and they are very different. So in case you age the sample and then started doing, for instance, DSR test or bending test, tensile test, what are you really testing? Are you testing the top layer or the bottom layer? Maybe the very, very bottom layer, if you have a thick sample of 1 millimeter or more, is not even aged. So what you're really measuring at that point, when you mix the whole age sample and start doing tensile or bending, all those tests, maybe you're just measuring an average of aging. The top layer is pretty aged, the bottom layer may not even aged. So now you're mixing the whole sample, you're gonna get an average, which is literally lower than the real aging level on the top. So now that we see the aging, we don't want this, right? It's not a pleasant phenomena. We don't like it. We don't like those wrinkles on the surface and all. So people think about rejuvenating. Can we reverse that? Can we go from the one on the right to the one on the left? So we're going to talk about rejuvenator in a minute. But one main reason of rejuvenation is we want to get all the good properties that we used to have. We want them back. How much we can get them back? It depends on the rejuvenator, on the type of application, and so forth. So let's say we have one rejuvenator here. We want to see how much it give us back all the good properties we want. And remember, now you are adding a new material. This is not asphalt. It's a new entity. It's a new modifier. Cover whatever you have lost during the aging. So here in the GSR, for those of you not familiar with GSR, is just a measure of shear resistance. So the higher the resistance of material to shear deformation, you get a higher modulus, complex modulus. It's done on an oscillation type test, and we name the test as dynamic shear rheometer. So regardless of the method here, we are measuring the shear resistance. And as you can see here, the shear resistance of the material in different hours of aging, 20 hours, all the way to 100 hours, shear resistance is different. It's expected, isn't it? A brand new material, or not even brand new, this is 20 hours. So 20 hours and then become 40 hours, then become 80, and then the one in the dashed line is 100. It's expected because you get the material more brittle, more stiff as you age it. Just looking at this picture, you get that same feeling, isn't it? So this become more stiff than this. So if I'm gonna shear it, this will shear easier than this, and that's what this test said. So the aging makes it go higher modulus. So if my rejuvenator is gonna work, what it's supposed to do, it's supposed to reverse it. Let's see what it does. So in this test, we actually have a measure developed by Glover Rowe, which look at the cracking resistance. If the sample that you have is above this red line, the solid line, that's supposed to be prone to crack. We call it severe cracking. If it's below the dash line, then it's safe. And as it gets higher and higher that way, upward, it becomes more prone to cracks. So when we want to improve it, we want to make sure it doesn't crack. Because literally, if the sample is up here and it cracks, and your rejuvenator doesn't move it downward, then you haven't really improved the crack. You may reduce the modulus a bit, but if it's still too high, they still could crack. So these are the one with the rejuvenator. We added this rejuvenator, and each one of these points, they just jump back. So the triangle here, jump back below dash line. The rectangular jump back here, the cross, and so forth. But you can see here the dash line, the red line here, the one with 100 hours, he didn't even care. He didn't even move. So the 100 hours aged material at that point was just aged to do any meaningful restoration. The other three, they did change. So there is some hope for them to get improved. But you can see the one after 100 hours did not even move. So that's one indicator of restoration. Obviously, if you have another measure, let's say now I'm showing you G star. If you have another measure, let's say you have the stiffness or a strength, crack resistance, any other indicator that you measure, if you know the results before aging or at a lower level of aging, you want your rejuvenator to give you back the good stuff you had. So conceptually, the meaning of rejuvenator is revitalizing the properties that is lost, revitalizing the characteristics that you no longer have. Another characteristics here I'll show you that might not be as in the spec or as common, but if you think about the material as asphalt as something that can heal, then you expect the one that aged, well, if the healing is lower, then you want your rejuvenator give you the healing capacity back. Here, I'm just showing the blue line as the aging progress. So we measured the healing at 0 hour, then 20 hour, 40 hour, 60 hour, all the way to 100 hour. You can see the healing capacity, which means if you actually create a tiny, tiny crack, you let the sample a rest period, it can heal itself. So concept of healing, which is actually a biomimicry way of thinking about material recovering. If you think about your skin, if you get a scratch or a cut, after a while, the cut is gone. Can the material, these are not live like us, can asphalt heal itself? Well, there are some healing capacity in asphalt, and it's been shown by different tests. When we create a tiny enough crack and let it sit, it can heal. So we measure that. There are ways to measure the healing capacity. And here you can see the healing is gone. After 80 hours or so, the material doesn't heal anymore because it cannot close the crack. You make the same damage into it and wait for the same amount of time as you waited for other samples, but this one doesn't close the crack. So healing capacity is gone or is reduced as aging progresses, and at some point is almost gone. So let's see what rejuvenator does. In this scenario, we applied the rejuvenator, and you can see at every point of time, we had improved healing a bit. for instance, here at 100 or 80, whatnot, it could shift it to sort of like at 80 is almost the same as 60. At 60 was almost the same as 40. So like we recovered 20 hours worth of aging. It's sort of like if I can make you 10 years younger. So this could make this material a bit younger. It could not make it to go back all the way to zero, but it was able to make it a bit younger. So the healing capacity was recovered to some extent. So some of the rejuvenator, some of you may be familiar with rejuvenators or what they are made of. A group of rejuvenators that are now in the market, there are some that are in research phase. My group have been working on a bunch of them. They're made from biomaterial and biomass. There are another group of rejuvenators that are paraffinic wax. There are aromatic group that are petroleum as well. Regardless of what their source is, we're talking about molecules. So if you're getting that specific aromatic structure from petroleum or from pine wood or from animal waste, that's a molecule. So sometimes you hear the category as categorization as bio versus non-bio. Well, that's fine, and it's nice to have something biodegradable because of all the carbon sequestration, reduction of fossil fuel dependence. Those are great things, and I'm very much advocate of sustainability. And my group has been one of the, I guess, active one in production of bio-based material and bio-based rejuvenators. But what I'm trying to tell you, molecules are molecules. They don't care where the source is. And I show you a bit of molecular modeling side to say, if I have an aromatic structure, for instance, or a fused aromatic structure that does this type of activity within the aged asphalt, regardless of where the source is, as long as it has the same number of carbon, the same ring structure, that will do that action. If it's from bio, that's one advantage, which is renewable, it's bio-based. So some of them are from waste, which is another advantage. But we have to separate those sustainability and bio-renewable side from the molecular efficacy of the action of rejuvenation. So here you can see from RAP up there, which stands for Reclaimed Asphalt Pavement, or RAS, stands for Recycled Asphalt Shingles. These are aged bitumen. Much like this picture I showed you that got all the cracks and wrinkles on top, these are 20, 30, some longer, sometimes 50 years or so aged asphalt, been on the road for many years. These are aged, highly oxidized. And now we want to reuse them, which is a great practice, but you have to make sure their properties are good enough not to compromise your new construction, your new pavement. So rejuvenator become more and more common and acceptable because we want to improve the properties of the new pavement and still use large portion of recycled material. Both win-win. You are recycling, you are using more recycled material, and you're still getting a super performance. That's awesome. So when you add the rejuvenator to your recycled material, on the aged asphalt. In another scenario, we add it to the virgin binder when we mix it with the asphalt in the tank. So either way, or the line that adds the other modifiers, it could also add the rejuvenator. So when you actually get the rejuvenator finally in your mixture, it's supposed to restore some of the properties that I showed you. So one thing that we have been looking at, because we always think about aged material being more prone to crack, one thing we always try to achieve with rejuvenator is crack resistance. One thing I want to caution you as you get to this topic or you research this topic, you have to make sure that you're not losing other properties that are not as much of, under as much attention. For instance, durability and moisture damage and aging trajectory. So if you pick a rejuvenator that does work and improve your crack resistance and your healing capacity, does it compromise your moisture damage? And now suddenly you get a asphalt pavement that it used to be not having any moisture damage, and now because you added rejuvenator, now it becomes moisture susceptible to moisture damage. That's something you have to keep in mind as you add new materials. I want to show you a bunch of rejuvenators because you will see many of them in the market right now. Of course, we show them with alphabetic numbers, so the names are not there, but the source are there in that table. You can see they're coming from vegetable oil, soy-based, they're waste animal, rubber wood, algae-based, many different rejuvenators. That's just the name. But really what is helping here is not the name, it's the molecules in each of this composition. And you can see here the aged material is the blue right here. And when we added all of this rejuvenator, they changed the complex modulus in different way. Here I put the unaged for you, so you can see the unaged and the aged. If I had the perfect magic that I could just convert aged to unaged, then I would get a curve like this, right? Unaged one. But as you can see here, all those curves have different slope, different amounts of distance or closing to the unaged. But one thing that is very noticeable, a group of them, which is in this dashed line, having almost the same slope, and another set did not even change the slope. So if you look at the slope of the blue, this violet, this blue, this green, they did not change the slope. That means the complex modulus versus phase angle did not change much. Yes, we did soften it, so complex modulus started coming down, but phase angle did not move forward as much. Ideally, we want this slope become something like this, like matching this curve, unaged. That may be impossible, but some of these, they actually change the slope and change the modulus together, which shows they are different. Obviously, there are different sources, different molecules in them. So I wanted to show you what made all of these guys different. Like the one I showed you, you may say, well, they soy-based. Yes, that's soy-based, that's based. They are different source, but Asphalt doesn't care about the name. Name is something we give to material. Asphalt cares about the molecule it sees when we actually inject it or dope it with. So the molecule that it sees are the one that attacks or gets to the aged asphalt. If you look at the first figure on the left, these are aged asphaltene. When the molecules of asphalt ages, you can see some of our publication on aging mechanism. What happens, your asphalt molecule become oxidized, an oxidized version of asphalt molecules, whether it's fused aromatics or the alkane chain, as they get oxidized, they become more polar. Increase of polarity makes them to adhere or bind together more often, and you end up having these stacks of asphaltene, for instance. Asphaltene tend to have pi stacking, and as we get more and more of them, you can see the layers build up to become a large aggregate. We're gonna have aggregated asphalt here. So aggregated asphaltenes need to be broken apart to get a format or conformation of the unaged status. On the unaged status, we don't have such large agglomerates because they're not as much polar to attract each other. In this case, the rejuvenator role is to get into those stacks and break them to smaller ones. I put this in a schematic to give you an idea of what's happening when you do the true rejuvenation. If you just add a bunch of liquids around this stack, the one on the left, you will get softer material, but you have a bunch of small molecules and you still have the same agglomerates right there, sitting there, nothing changed. That is still soften your material, so you get lower modulus, but you don't really recovering the properties, you don't revitalizing it. The true rejuvenator in our group's position is that we need to deagglomerate the asphaltene aggregates, and the deagglomeration is only possible with some of the molecules. Not every softener can break the agglomerates. So the rejuvenator has to have the capacity to break down this agglomerates by diffusing into the structure and then causing enough steric repulsion to push these aggregates away, and ultimately you get smaller aggregates. This is just an schematic, but I'll show you some of the simulation as well. So deagglomeration is the mechanism we think is causing or leading to true rejuvenation. And here is some of the results of the simulation. We basically did the asphaltenes and let them aggregate after aging. In the simulation box, you can see this circle here. And as the rejuvenator broke them apart, they become intercalated into that asphaltene structure. So now you see the green lines. Green molecules are the rejuvenator that are getting inside this asphaltene nano aggregates and breaking them apart. How can I measure it in a bigger scale? What I'm showing you here is, of course, molecular dynamic simulation at molecular level. How can I measure this phenomena in a macro level? Obviously, I can't do it by naked eye. I can look at it and see if it's deagglomerated or not. So we did a lot of tests to find an actual macro level test that can connect what is happening in the molecular level. Here you can see the crossover values. And for those of you not familiar with the crossover parameters, is when you measure modulus and frequency, you have, because this asphalt is viscoelastic, it has viscous and elastic components. And that's why we always plot any property, modulus property, elastic modulus we call it, or complex modulus, against phase angle or against frequency, because the asphalt is frequency dependent. You can measure the property of asphalt to be X at one frequency and be Y at another frequency. It's not like an elastic material. You have to always look at the frequency at the same time. So when you look at the elastic modulus and viscous modulus, there is a point, there is a frequency point that the two of them are equal. That one called crossover modulus. And the frequency at that, the two values are equal, basically modulus, elastic modulus and viscous modulus, we call that crossover frequency. When we measure the crossover modulus and crossover frequency, for all those rejuvenator, you can see these numbers here. Crossover modulus was a very good representative for the deagglomeration and is actually relevant to polydispersity. This is also published in our paper on aging and polydispersity. Has a different polydispersity than when they are agglomerated. So here in case of, for instance, rejuvenator A, you can see the increase, the change here. Unaged was crossover modulus was 3.3. It was totally almost gone when it was aged. It reduced to 0.5. So if I want to restore it, I want to get 3.3 back as a sign of polydispersity or measure of the agglomeration. In this scenario, only 3 green ones, which is A, D, and L, they managed to bring it up significantly, and B actually reduced it, or didn't change much, but reduced it a bit. And W did not change. So when we were looking at the agglomeration, and I mentioned before how the modulus changed, there are properties that are indicator of true rejuvenation, and some, they're all softeners. So if you look at all of these rejuvenators, they all soften. So if only you look at softening, they will be all good softeners. but only some rejuvenate, which means they recover and de-agglomerate asphaltenes. Otherwise, for the softening, you can use any of this A to L rejuvenators in the market. So increasing both crossover modulus and crossover frequency was an indicator that is doing the right thing, because we wanted both factor to go toward on age. So 3.3 here, 1.59 here, and you can see only some of them, they actually increase. So A here increase both, D increase both, and L. So these were the one that increased both of them, not only one of them. And we use that measure to indicate or define which one is more closer to a true rejuvenator. Then one other thing is actually when you look at the different scenario here for aged rejuvenated asphalt, the modulus and frequency here, we studied them with the actual wrap. So we got 25% wrap and 75% virgin material. And in one scenario, we had 100% wrap. All of those scenarios, you can see the change as the rejuvenation was taking place. This is actual wrap from the road. So effect of rejuvenator in Arizona aged asphalt was very noticeable. And when you think about Arizona's aged asphalt are highly aged because we have many days of sun and high temperature of above 100 Fahrenheit. And so in this case, we actually get very aged asphalt. And you can see here how the rejuvenators work for crack propagation. Crack propagation here on the green side, you can see the slope of the green, and then you can see the control plus rejuvenator. They are different in terms of their category. So you can see it reduced the crack propagation. It also improved the energy that requires to propagate the crack. That's basically a test we use as a crack propagation as a function of crack length. One other test that I want you to also pay attention if you end up working with different rejuvenators is always about moisture. Because many of the rejuvenators, especially those that are bio-based, they may have molecules that are moisture susceptible. So in this case, we had two scenarios, and you can see in the previous slide, I mentioned A, D, and L were the one that changed both crossover modulus and crossover frequency. So now we are just looking at this tree. And when we actually did the Hamburg, only L could go to 20,000 cycle for the stripping inflection point. The rest of them were lower. And the funny enough is the extracted binder, which is the aged binder itself, it was 20,000 plus. So aged asphalt here, extracted binder, aged asphalt, did not have any problem. When we rejuvenated it with A, now we get 13,000. That means it's more moisture susceptible than the aged asphalt was. When we added D, same thing happened. Only L did not reduce the number of cycles at the inflection point. And the inflection point here is used as a sign of stripping. And you can see here with the schematic, when the inflection point is happening, you get two slopes. So this is a creep slope here, and then you have a stripping slope. The cut here will tell you how many cycles it takes to get to this inflection. And in this case, aged asphalt had 20,000 cycles before it get to the inflection point. So you can clearly see that A and D and L, based on crack resistance and modulus and all these other factors I told you, they were good. But when it comes to moisture, A and D actually made it more moisture susceptible. And so far, from all the lists that we started with, only L pass the moisture resistance test. So of course, for rejuvenation and true rejuvenation, we need a reliable test. And in this case, to connect the molecular phenomena, whether you measure it or simulate it, it doesn't matter. There is something happening at the molecular level. It doesn't matter if you see it or you can measure it or not, it is happening. So if we have a test that reliably connect molecular level to macro level, then we can truly measure rejuvenation. So in this differently. So I put some reference here, I put some reference here in case you are interested to look at some of the work that I basically summarized here. And I want to give you some time to ask any question. This work is sponsored by National Science Foundation here in the US, and part of the work was also sponsored by our project with Arizona Department of Transportation. So I want to give time to the question and answer. Ellie, you have the podium.
Yeah,
back
thank
to you.
Yeah, thank you. Thank you so much, Dr. Fini, for a very excellent presentation and very informative presentation and details about the rejuvenators in very, very deep knowledge about that and how we should care and take care of them when we want to use rejuvenator, the right rejuvenator in the asphalt to make it revitalize aged asphalt. Yeah, thank you so much. Really, lots of information we got and from this presentation. Yeah, I just got one question till now. I ask everybody if anyone has also question, please don't hesitate. Yeah, please type your question and I will read them and Dr. Fini will ask them. Yeah, I received one question is asking about, does there exist anything in organic rejuvenators that makes them more effective than petroleum rejuvenators?
That's a very good question. So it's actually a very smart question, because when you're saying, is there anything in organic rejuvenator, you're talking about molecules. Because one name is organic, one is non-organic. Yeah. Right? So the difference is what is in it. The name doesn't matter. So to answer to your question, yes, it does. And some of these molecules that we extract from bio sources, they have a significant amount of fused aromatic rings, which helps with the unlocking of aggregates. We actually did look at different molecules and how they can deagglomerate. If you give me long chain, fused aromatic, cyclic, with side chain, without side chain, each one of them have different capacity to deagglomerate. And some of the bio sources we have looked at, we have more of it. So you may get aromatics from petroleum, but they are more or less same structure. You don't have that much of a diversity that you get in bio. But that being said, I'm not generalizing all the bio sources, because same, you know, as we name them differently, they are actually chemically different as well. So if you get one thing from pine wood, it's different from walnut, it's different from poplar, it's different from animal waste. So each one has different molecules, but you got the point right. They have different molecular structure, and some of the bios have very promising molecules.
Okay. Yeah, great. Yeah, thank you. Thank you so much for your answer. Yeah. And yeah, another question is about how to measure the viscosity at 60 degrees of rejuvenators in DSR with plate-to-plate geometry.
So to measure the complex viscosity, you can always use DSR at, depending on the stiffness of your sample, you can use different temperature. So the reason we actually use parallel plate And most of you familiar with 25 millimeter or 8 millimeter. These are just to allow us perform the test, because each machine has a limited torque capacity. If the material is too stiff, you can't even use the machine. So we, based on how stiff your sample is, you have to adjust the spindle size and temperature to fall within the torque limit of the machine. I give you an example of if you're testing a honey, and if you're, in the morning when you're trying the honey, take it from the fridge, you can see it's harder to pick a spoon of honey. Leave it sometime outside, it's easier to take a spoon out of honey. That's called shearing. So if you feel it's stiffer, that means the machine feels stiffer. And each machine has a limit. So to answer to your question, you can measure it at 60 depending on the machine that you have. And if you feel it's difficult or it goes above the torque limit, you can use a smaller spindle. We do even have cone and plate instead of parallel plate, which allows smaller samples.
Okay, great. Yeah. Thank you. Thank you so much, Dr. Fini. Yeah, any question? Any other question from audience and from the attendees? Yeah, I received another question about how can we ensure about enough diffusion of rejuvenator with aged binder?
Great question. So when you actually mix your rejuvenator into the virgin bitumen, diffusion is facilitated because of high temperature and liquidity of the virgin bitumen itself. And most rejuvenators that I'm familiar with are liquid anyway. And most often they have much lower actually melting or if it's meltable or boiling point than asphalt. So mixing them in virgin bitumen, it's fine as far as diffusion. If you're talking about spraying it on top of the recycled asphalt or reclaimed asphalt, diffusion could be a concern because aged asphalt is pretty stiff. And in that scenario, you actually need molecules to be very active in terms of diffusion. So mobility of each of these molecules that I showed you for rejuvenator is different. Diffusion literally is a mass transfer. If you have a ping pong and you're moving it with your finger from one point to another, or you have a basketball moving it from one point, you feel the different force, the difference in energy to move this. Same phenomena applies to diffusion. The one that move easier, whether it's smaller or it's more mobile, that has higher diffusion. So when it comes to spraying directly on the wrap, you have to make sure you get enough diffusion to be able to be effective. And each molecule has their own diffusion rate.
Right. Thank you. Thank you so much, Dr. Fini. Yeah. Any other question? Yeah. Okay. It seems, yeah, no more question. Yeah. Thank you so much, Dr. Fini. Yeah.
Ali, let me just add one thing for the student or the person asked about the measurement at 60 degrees C. You can email me to send you some reference for how to measure viscosity at a constant shear.
Okay, yeah, that's good. Yeah, sure. Thank you. Yeah, I got also another just question now that asking about can chemical composition investigation help to select right rejuvenator or crossover and frequency?
Well, chemical analysis is always a better way in doing things, but we are not always equipped in all asphalt lab to look at the chemistry. So we actually, most asphalt lab prefer blind chemistry tests. That's why we always try to connect the chemistry in the back end to a macro level or a mechanical test, and DSR or rheometer is a mechanical test in the front. So if you can connect, right now we try to connect crossover values to chemistry. So you don't actually need to go back and do all the FDIR and look at the molecular diffusion and all this. check your rejuvenator to see if the crossover modulus and crossover frequency, both of them increase. If only one of them increase, you only have a softener. If none of them increase, you don't have nothing. And many of rejuvenators, they only improve one. And then after you decided, yes, it does the work, go ahead and check for moisture damage.
Great. Okay, great. Thank you. Thank you. Very great. Okay, so any other question from attendees? Okay. Yeah, it seems, yeah, that's all. I think, yeah, no more question. Yeah, thank you so much, Dr. Fini, for your time. Very nice presentation and answering the question. Yeah, I think it was very, really informative, and we got many information about the rejuvenators and how we make sure that we use the right one in the agent as a binder. Yeah, thank you. Yeah. Okay, so I think with that, we can wrap up our today presentation. Just please don't forget that our last session, the series of this lecture series, will be on 27th of December at 10 o'clock Beijing time in the morning, with the title of Mechanism of Moisture Damage in Asphalt, which will be presented by Dr. Fini. For your presentation. Yeah, thank you so much, and happy holidays to everyone. Yeah, thank you, Dr. Fini.
Thank you, everybody. See you next time.
Yeah, see you everybody. See you everyone next session. Yeah, we are waiting for everyone. Yeah, thank you.